If you ever studied physics, or even if you didn't, you might have heard the word entropy. It was probably described to you as a measure of disorder or uncertainty of a system, but that doesn't really tell the whole story. It turns out that entropy is intimately related to temperature. Today I want to try to expose the relationship, starting from first principles, in what I hope will be a more intuitive way of thinking about thermodynamics. Towards the end, I will also show how it's possible to have a system with negative temperature, as in below absolute zero, and what it actually implies. To understand what we aim to do, let's say a friend of yours challenges you to a bet. He throws 2 dice and wants you to guess the sum of the numbers on top of them. What's the best possible answer? Let's start by noticing that not all the values have equal probability. There is only one way for the sum to be 2, 4 ways for the sum to be 5, and 7 ways for the sum to be 7, which turns out to be the best answer. In the branch of physics called statistical mechanics, we have the opposite situation. We have a system of multiple particles. We don't know their energies, but we know that their sum has a certain value, which will stay fixed if we isolate the system. And we wonder how valuable is this information. But as with the case of the dice, the answer changes for different values of the total energy. To dive deeper into this fact, we'll consider the case of a very simple particle, for which only 2 states of energy are allowed. The particle, which I'll show with a circle, can either have energy 1 or 0. We want to consider a system of n of these particles, for example 7. We can choose a value for the total energy of the system, let's say 3, without knowing how this energy is distributed among the n particles. If we isolate the system, the state of the particles can change as they interact with each other, but the total energy of the system will remain constant. In our case, there could be many possible configurations of particles. But how many exactly? With energy equal to 3, we need to choose 3 particles to fill. We have 7 possible choices for the first one, 6 for the second, and 5 for the third. But our particles are identical, and that means that if we number the 3 white particles, all the permutations of them will have to count as one unique state. So we divide by the possible ways of combining the 3 particles, which again is 3 choices for the first, 2 for the second, and 1 for the third. You might recognize the denominator as the factorial of 3, and we can also write the numerator in terms of factorials, where the 4 is just 7 minus 3. Then we can generalize the formula. These are the numbers of possible configurations for each energy value. For the case of 7 particles and a total energy of 7, there is only one possible way of distributing the energy in the system, so that we have no uncertainty. But in general, the more configurations are possible, the less we know about the system at that energy state. We want to relate this uncertainty to temperature, so let's think about what happens physically. Let's consider 2 objects of the same material, starting with the same internal energy, one much bigger than the other one. If we supply the same amount of heat to both objects, you can probably guess that the temperature of the biggest one is going to be raised less than the smaller one. Let's now consider what happens to the number of possible states. Let's say that the bigger object has 25 particles and the smaller has 4. If we start with energy equal to 1, we can calculate that the first system has 25 possible states, and the second has 4. For brevity, I called the number of states omega. If we supply heat, or in other words, energy, to raise the total energy to 2, the first system can now have 300 possible configurations, for an increase of 275, while the second can have 6, which increases the number only by 2. So to summarize, we have that the supply of energy corresponds to a smaller rise in temperature for the first system than the second, but the opposite is true for the number of possible states. But how are the two related? Temperature is the quality that two bodies share when they are at equilibrium with each other, so let's consider the case of two systems, one with 3 particles, the other one with 4. We'll set energy equal to 2 for the first and to 1 for the second. If we put them in contact and let them exchange energy, the sum of the two energies will stay constant, but energy will flow freely from one system to the other. New configurations are possible, which weren't possible before. The first system might have all the energy at a certain time, or the same could be for the second system. If we fix the energy of one system to be 1, we know how to calculate the number of possible ways this could happen. The point is now to notice that the energy of the second system must necessarily be equal to the remaining energy, which is 2, or 3 minus 1. We multiply the two numbers, and since we fixed the energy of the first system at the beginning, to have the actual number of possible states, we need to sum over all of the possible values for E1. If we visualize the terms of the sum for our system, that's what they look like. Now, we are interested in systems of many particles, like the ones we encounter in everyday life. So we make the system bigger and bigger, and we see what happens. We see that the sum concentrates around the value, the equilibrium state, which also corresponds to the maximum term of the sum, or, in other words, the most probable. From now on, I will simplify the term of the sum by calling the first part omega 1 and the second omega 2. To find the maximum of this product, we set its derivative equal to 0. This equals the derivative of the first term times the second, plus the first term times the derivative of the second. We then use the chain rule of derivative, and the fact that the change in E2 is the same as a change in E1 but in the opposite direction, because energy must be conserved. We now divide everything by omega 1 times omega 2. We simplify and we move the negative term to the second member of the equation. We also include the 1 over omega into the derivative as a natural log. This quantity must be the same for the two systems at equilibrium, so it might be temperature. To match this with real temperature, we multiply it by the Boltzmann constant and we define this quantity as 1 over temperature. The quantity in the derivative is instead defined as the entropy of the two systems. To sum it all up, let's see what this means. We consider two systems. This time we plot the entropies in place of the number of states. We let them start at different values of the energy. We consider the slopes of the graphs at those initial points. We now know it to be the inverse of temperature. When the two systems come into contact, they will approach the same equilibrium value. To understand what negative temperature means, we first notice that if we supply energy to the system while it has positive temperature, the entropy will increase. But if instead we consider the case of negative temperature, entropy will decrease as we supply energy, making it possible for order to emerge at high energies. And this actually has many cool applications in physics, including, for example, lasers. I may even make a whole video about this in the future. For now, I just wanted to show the relation between entropy and temperature from a different point of view.